Hello viewers, today we will talk about the solution of transmission line. When we want to the solution of transmission line means we have to find the expressions of the voltage and current that will give the value of voltage and current at any point at any instant on the transmission line. Today's lecture we will cover that what is the solution of voltage and current at any point of Z on the transmission line. We assume that the transmission line is propagating along the Z axis. The transmission line secondary parameter which is called the propagation constant, what is the loss of the line, how much phase shift is take place, voltage and current distribution along the line, characteristic impedance and the effective impedance of the line. A transmission line is represented in terms of the transmission model in which each sections having a effective resistance, inductance, capacitance and conductance. So, the whole line is a cascading structure of these RLGC parameters. To solve the line, we will applied the Kirchhoff's voltage and current laws, although we have to mention here that this current Kirchhoff's law is valid when the length of the transmission line is very less in comparison to the signal propagation or wavelength. So, here we can see that the line is symmetrical all around the length. So, we have to do the analysis only for a single section of the transmission line. So, the topmost figure shows the single section of the transmission line that is having the component R, L, G and C. These units are having per unit length. So, the section's length is we have taken del x, the value of these parameters is multiplied by del x to find out the net value, and for each section suppose we applied the voltage V and the change in voltage take place when the voltage or the signal is transmitted the single section by del V. Similarly, the current at the input side is I and it is changed by del I. So, to find out the change in voltage across this section, we have to see the current is constant throughout the section and the change in voltage is given by the series resistance, that is R plus j omega L, and that is multiplied by del x and then give the current. The voltage drop is negative because we are reaching the left hand side is ascending end. So, the voltage drop is there. So, there is a decrement in the voltage. Similarly, due to the shunt path some current is passes and the current is continuously decreasing. So, the change in current in the section del x is given by the current through the shunting path, the reactance or admittance of the shunt path is G plus j omega multiplied by the voltage V is constant, we have assumed constant because the length is very small. So, from this expression we can find the dV by dx and di by dx, and if we have to see the approximation that this del x is very small and even when the limit of del x tends to 0, this expression becomes the differential equation that dV by dx is minus this. If we again differentiate the equation R dV by dx or the second order differential equation with respect to x and put the value of di by dx, we are getting the equation that del 2 V by del x square is equal to R plus j omega L first factor series impedance and the G plus j omega L series admittance multiplied by V. This is a second order differential equation and the propagation constant gamma square which is equal to the product of the series and shunt admittance, that is gamma square is equal to R plus j omega L and G plus j omega square. This gamma square is called the propagation constant and a second order differential equation. This gamma or the propagation constant, we can see that from the expression it is a complex quantity, and we can equate this gamma is equal to alpha plus j beta. The value of this alpha and j beta, that depends upon the RLGC parameter as well as the operating frequency. The second order differential equation always represent a propagating signal. Here the signal is electromagnetic signal or voltage or current that will oscillate along the transmission line. So, the transmission line solution means we have to solve this second order differential equation. The general solution of these transmission lines is we can express in terms of that V equal to C1 e raised to power minus gamma x and C2 e raised to the C1 and C2 is the constants. The value of this constant can be found out by applying the boundary conditions for the transmission line. Similarly, the solution of the general solution of the current is given by this equation. This gamma, that is we have used in the last slide, that the gamma is a complex one, and especially if we try to apply this solution for our harmonic variation signals, that is the voltage and current is sinusoidally vary. So, the V of t is V 0 is j omega t, then the solution can be modified as given by this V of t equal to V plus exponential of j omega t minus gamma x plus V neg. These are the maximum value of the voltage and exponential of j omega t plus gamma x. Similarly, the solution of the current is given. From these expressions, we can find that the solution is having two terms. The first term in which j omega t minus gamma x and the second is j omega t plus gamma x, they represent the two signals, one is forward wave and another is backward wave. From where the backward wave is coming, when we applied only the signal at the shore side, actually when the signal is propagating and if any kind of discontinuity is there, impedance mismatch is there, part of the signal is reflected back, that is the source of the backward wave. It is not necessarily always the backward waves exist, it depends upon the mismatch conditions. So, the solution is general, it includes the both forward and backward waves. When we put the gamma or our propagation constant as alpha plus j beta, then the general solution we can find. The solution having each solution, for example, the first term will have the exponential terms and the sinusoidal terms. So, the exponential minus alpha x will represent the decrement or attenuation of the signals when the signal is propagated from the source to end side, and the second is sinusoidal signal, that is the oscillating wave that is moving in the direction of x here. Similarly, the current is also a oscillatory wave and its magnitude is decreasing. We are measuring the distance from the shore side. So, we can see the backward wave having the coefficient of exponential positive alpha x, that means the magnitude of reflected wave is maximum at the load side and it is decreasing toward the shore sides. The picture will represent the form of VI solutions, that when the line having some attenuation, the red one represents the magnitude component, that exponentially the signal is decreasing when it is moving along the line, and the blue one shows the oscillatory or sinusoidal variations. So, the wave is moving. This solution having a general term, that means the line is provides some attenuation and as well as the line is propagating the signal sinusoidally. if we try to find out the value of alpha and beta, alpha is the attenuation and beta is the phase shift constant, then from the expressions we can find separating the complex and imaginary part when we do the square of the first equation, and then by equating the imaginary and real part separately, we can find the general solutions of alpha and beta, which are ultimately depends upon R, L, G, C and the operating frequency omega. So, it depends upon ultimately on the line parameter, and the line parameter depends upon the physical dimension of the lines. The attenuation constant is provide the attenuation per unit length, its unit is Napa per minute, and the imaginary part, that is beta, that provide the rate with which the signals phase shift is take place when it moving along the unit length. So, there are total 4 parameters, primary constant RLGC of the line, and the secondary constant. In terms of that, we measure the performance of the line, gamma, alpha, beta and Z0. Z0 is the characteristic impedance, and we will define in the next slides. Now, let me see the special case when the line is lossless. That means, the resistance of the line is 0, the conductance of the line is 0. So, from the expressions we can see that alpha will be 0 when R and G is 0, and the beta is given by omega under root L C. At that time, the exponential decaying term will be 0, and the signal's magnitude remains constant when it propagates from the, so as shown in the diagram. The line is distortionless. Again we will see that when the line is distortionless, that means the line's distortion is basically when we propagate a communication signal and the shape of this signal is distorted, then the line is provided the distortion. When the signal is distorted, if suppose there are multiple component of frequency is there, each component having different attenuation, then they are not able to maintain the shape of the signal. That means, the line's loss is function of frequency, line's phase shift is also function of frequency. At that time, the line is also distort the signal. To remove these distortions, if we try to see from these expressions that if we provide the condition that L by R equal to C by G, then the propagation constant can be expressed as gamma is equal to under root of R G multiplied by 1 plus j omega alpha. So, the real part which is alpha is under root R G, and now this is not function of omega. So, all frequency component having same attenuation, then there is no distortions, and the phase shift, that is linear function of the omega. So, this kind of line is called distortionless line. The other parameter on the transmission line, that what is the velocity of the signal's propagation. When the wave is propagated, basically at every point and every instant the phase of the line is different. So, if we try to put the omega t minus beta z is equal to constant, then we can find the speed of the signal. We also defined it is phase velocity, and if we try to find out the dz by dt, the rate of phase shift along the line, it is given by omega by beta, and that is given by 1 upon under root L C, especially when R and G is 0 for the RF line. So, this is the phase velocity. This gives the velocity by which the voltage and current propagate along the line. This omega is not depends upon the media, then the media is called linear media, and if somehow this phase shift is also depends upon the operating frequency, then the line, or at that time we have to define the group velocity. Multiple frequency components when they are moving, they have a net speed that is differ for different component, for especially when we have provide the modulated signal in this signal wave, then the signal having a frequency component of f1 to f2. So, what is the average velocity with which this pulse is propagating, we will define the group velocity. The points on the transmission line over which the total phase shift is take place by 2 pi or a full cycle, we will define the wavelength lambda, that is 2 pi by omega under root L C. The next is characteristic impedance of a line. The ratio of voltage and current at every point on the transmission line is called characteristic impedance. This is given by V plus forward wave, V plus divided by I plus, and similarly for the backward wave this is given by V I plus and I plus. This characteristic impedance is not depends upon the position of the line, and from the previous expressions we can find the Z0, that is the characteristic impedance, that is given in terms of the primary constant of the line. So, that Z0 is again depends upon the physical structure of the line, and when the line is lossless, R and G are 0, the characteristic impedance is given by the under root of L by C, and it depends upon the self inductance and capacitance of the line. These characteristic impedance, we can also find that it is the input impedance of a line when the line length is infinite. Practically infinity means the line length is more than 10 times of the length of, we can assume it is an infinite line. At that time, if you measure the input impedance at the input line, that is coming out equal to the characteristic impedance of the line. And the input impedance of a finite length line, that is depends upon the position of the line, and the ratio of voltage at that point to the current at that point is given at the input impedance of that line. And this general expression again we can find by the general solution of voltage and current, and this is given by this: if the line is lossless, this hyperbole cos gamma L, and this will become the tangent functions alpha 0, the gamma will be only equal to j beta. At that time the input impedance of the transmission line is coming out Z0 times of ZL plus JZ0 tangent beta L divided by Z0 plus JZL tangent beta L. That means, the input impedance is a kind of impedance transformation. For example, at the load end we connected the load ZL, and if we measure the input impedance of a line at length L, then the input impedance is different, and it is given by this expression. So, it is function of the characteristic impedance, function of the load that is connected to the line, and the function of the length of the line. The input impedance of the transmission line, if we assume the special case that the line is short circuited, at that time ZL is 0. So, from this expression we can see that the input impedance is for the short circuit is coming out j Z0 tangent beta L, and when the line is open circuited, that means infinite load impedance is connected, at that time the input impedance of the line, that is called ZOC, is given by this. So, these two expressions we can see that the input impedance of the line is only reactance, this is not resistive parameter. The line is lossless at RF frequencies. So, a section of the line which is short circuited or open circuited will represent either capacitive inductance or inductive reactance depending upon the length of the transmission line, and the variation of this is periodic along the line. So, we can see that either infinite, short circuit or 0 reactance will be provided by the line when the length is different at different point. Today we have found the solution of the voltage and current along the transmission line, and we found the attenuation constant and phase shift constant. Those are depends directly on the primary parameter of the transmission line. We also defined the characteristic impedance of a transmission line, and we also found the input impedance of the transmission line at any point. The characteristic impedance is especially depends upon transmission line's dimensions, and it is unique for a transmission line. Thanks. I hope you have enjoyed the lecture.